Alright, in this Regents chemistry video we're going to talk about collision theory and rate of reaction. So collision theory is basically this idea that in order to have a reaction we need the particles to collide with each other. So that's very important, that if we want the particles to react they have to have some sort of interaction with each other in the form of collisions. So they have to collide with each other in order to react. That's very important. So a reaction is most likely to occur based on collision theory if the reactants collide with the proper energy and the proper orientation. So this means that in order for a reaction to occur, the particles have to collide in a specific way. So if we look at this diagram down here, the first example is of a proper collision. So if we have A and B colliding in a way that would possibly give us A and B, so you can kind of just tell that they're lining up here in the proper way. If we want A and B like this, we're kind of getting that from this orientation here with A and B, and then they can kind of split off and go like this, right? So this makes sense based on the orientation. If we want these AB molecules like this, it wouldn't make sense to have them collide in this way, right? Because A is going to kind of come in here and it doesn't really line up like it did here with these two separate AB interactions, and so it's not going to have a reaction. So this is what we mean by orientation, is that they just need to be lined up right. And with the proper energy, we basically want them to be coming in. Remember, the particles are all going to be moving with this kinetic energy. We want them to have a certain amount of energy. If there's not enough energy, then we won't be able to have a reaction. So again, collision theory, just know that reactants are going to react if they collide with the proper energy and orientation. So in terms of what this means for the rate of a reaction. A rate of a reaction tells us how fast it's going. Basically, how many times are we completing this reaction in a given time. So it could be completions in a certain amount of seconds, or usually you will say in terms of concentration, molarity per second, or something like that. So it's basically just measuring, again, per unit time, how fast is this reaction going. So any rate is telling us how fast something is going per unit time, how much of whatever we're doing. If it's speed, how much distance are we covering over time. In this case, we're saying how much is the concentration, the molarity, changing over time. So if we have this reaction here, we're saying how many completions of this reaction, how many times are we going to react one of these with two of these to make one of these and two of these. So how many times are we going to make this reaction go every second or every minute or every hour, whatever time frame we're looking at. So again, it's just a measure of how fast it's going. So in terms of collision theory, this matters because the rate can be expressed in terms of the reactant concentrations. So we have the same equation here. For every one completion of this reaction, every time we do one completion of this reaction where we react one of these with two of these to make one of these and two of these, right? The rate of the concentrations of individual reactants is not going to be the same as the rate of the overall reaction, because every time we complete this reaction we're using up two oxygen molecules and making two water molecules. So the rate of formation of H2O in this equation specifically is 2 times the rate of the reaction, because for every one reaction, RXN being an abbreviation for reaction, one reaction is giving us 2 H2O molecules. So the rate of H2O formation here is twice the rate of the reaction, because we're getting 2 of these H2Os for every one time that we do this reaction. So the rate of formation of CO2, on the other hand, because it's a 1-to-1, every one completion of the reaction gives us 1 CO2. This is going to be 1 times the rate of the reaction. So basically, because this is a 1-to-1 relationship, every completion of the reaction gives us 1 CO2 molecule. The rate of formation of CO2 is going to be the same as the rate of the reaction. If we look at O2, the rate of disappearance, because it's a reactant, we're using it up. So this is going to be 2 times the rate of the reaction, because for every one completion of the reaction we're using up 2 O2 molecules. So the rate of oxygen consumption is going to be twice as much as the rate of the reaction. And if we look at CH4 again, the coefficient here is just 1, so this would be equal to the rate of the reaction. or 1 times the rate of the reaction, because again it's a 1-to-1 relationship. Every completion of the reaction uses up 1 CH4 molecule. So in terms of the individual concentrations, we could also relate them to each other. We could say the rate for, let's say, O2 would be 2 times the rate for, we could say, CO2, because again the oxygen has a coefficient of 2, so we're using up 2 for every 1 CO2 we make. And then because we're using up oxygen, it's going to be decreasing, so we could put a negative sign here to reflect that 1 is going to be increasing, the CO2, right? It's going to be increasing because it's a product, we're making it. The O2 is going to be decreasing, it's a reactant, we're using it up. So the rate of O2 times -1 would give us 2 times the rate of CO2. So because we're using the O2 up, it's going to be decreasing. Because we're making the CO2, it's going to be increasing. And then the CO2 is going to be half the rate of O2, or the rate of oxygen will be double the rate of CO2, because again we've got this coefficient of 2 here. So in terms of collision theory, how is this going to affect the rate? If we have O2 being consumed at a rate of 5 molar per second, so this is again a concentration per unit time, what is the rate of formation of CuO? So we have 5 molar per second of O2, and we're trying to find what's going to happen to CuO. So this is going to be very similar to the stoichiometry conversions that we did before. So we're seeing what is the relationship between O2 and CuO. So again, we have O2, we'll put that on the bottom so that it cancels out. We're looking for CuO. So all we have to use here is the coefficients in this reaction. So if we write this reaction out, we have it visually here, but it would be 2Cu plus 1 O2 makes 2 CuO. So this is a balanced equation, right? We've got the 2 coppers, and the 2 coppers, we've got the 2 oxygens, and the 2 oxygens here. So this is a balanced equation, and then we've got the written form here. So the relationship between CuO, which has a coefficient of 2, and oxygen, which has a coefficient of 1, would be 2 to 1. So we cancel out oxygen with oxygen here, and then we would end up with 10 molar per second of CuO. So because the rate of formation of CuO, we're making this at twice the rate that we're using up oxygen, because again we have 2 of these and only 1 oxygen molecule. There's 2 atoms here, but 1 oxygen molecule, which is the molecules that we're looking at. So we're making the CuO at twice the rate that we're using up the oxygen. So we again just use the coefficients just like we did with the stoichiometry conversions, and here we get 10 molar per second for the rate of copper oxide here. Alright, so finally here we're going to talk about collision theory and how that affects the rate, how certain factors will affect the rate. So all we have to do is think about how these factors affect the collisions, because the collisions are what make the reaction go and therefore affect how fast it's going to go. So if we think about 2 sets of molecules, like if we look at maybe this box down here, and we think about how would temperature affect the rate. Well, the rate is how fast we're going, right? And the collisions are, if we have these molecules colliding with the proper orientation and energy, then they are going to be able to react. So how does the temperature affect that? Well, the temperature measures the kinetic energy of the particles. We've talked about this during the energy unit, right? That these particles, if they have a higher temperature, are going to be moving faster, right? So if they're moving faster, they're going to be able to collide with more energy, and also they're going to be able to collide more often, because if these are moving around faster here, they're going to have more opportunities to collide. If they're moving around very slow, then they're not going to collide with each other very much. So as temperature increases, then the collisions will also increase. So if the collisions are increasing, therefore the rate will be increasing as well, because if we have more collisions, more frequent collisions, that's going to enable the reaction to go more effectively and faster, which is going to increase the rate. So as temperature increases, the rate will increase, because again it's all about the collisions, and because we're going to have more collisions, that will make the rate higher. So what if we look at the surface area of the reactants? Let's say we maybe have a cube of a certain substance, and then we maybe also have like a powder of the same substance. Which is going to react faster? Well, we're talking about the collisions here, so if it's a surface area that's larger, there's going to be more opportunities for collisions. More of these molecules are going to be able to collide with each other if more of them are exposed, right? If we have a cube here, there's going to be a whole bunch of molecules in the middle of the cube that aren't exposed to whatever this outside external reactant is. Let's say we're going to drop this cube in some sort of liquid and then have it react. These little particles in the middle here aren't going to be able to react with that liquid because they're not going to come into contact with it until the outer area of this cube is kind of worn away or reacts or whatever ends up happening to it. If we drop a powder into the same liquid though, then what we would have is all of this exposed material here, which would be able to collide with all of the liquid or solution or whatever this actually is. This is going to have a lot more opportunity for collisions because it's a lot more exposed. So as surface area, and I'll abbreviate SA here, as surface area increases, the rate also increases because we have more of an opportunity for collisions. A higher percentage of this substance that we're kind of putting in here is going to be exposed, is going to be available for collisions. If it's in the center here, it's not available for collisions with this outside stuff because it can't come into contact with it. It's kind of blocked by the outer shell of this cube in here. So as surface area, rate increases again because we have more of an opportunity for collisions. So the last thing here is in terms of the concentration, what happens to the rate. So if we increase the concentration here, so this is where I'm going to clear all this stuff out now. So this is where if we're going from low concentration to high concentration, then what's going to happen to the rate? Well, if we have a higher concentration, there's going to be more particles per unit volume, right? So we have pretty much the same volume here for these two situations, and what's the difference? Well, the difference here is we have a lot more particles moving around in here. They're a lot more crowded, so that's going to lead to higher collisions. Remember, we're always just thinking about the collisions in terms of the rate here. So if we have a higher concentration, there's going to be a lot more crowded space in there, so they're going to collide more, right? If you're, let's say, in an elevator with a bunch of people, you're a lot more crowded in space, you're more likely to bump into some of them, whereas if there's only two people in the elevator, you're not as likely to bump into each other, right? So it's the same idea here. We have a lot more particles, a higher concentration, they're going to collide more, and that's going to lead to a faster rate because it's all about the collisions here. They're going to collide more if there's more of them in a tighter space. So as concentration increases, rate also increases because, again, in terms of the collisions, we're going to have more collisions because of that more crowded space. Alright, I hope this video on collision theory and rate was helpful, and I'll see you in the next video.